Alright, AP Physics 1 students, don't worry. I've gotten your emails. I've gotten your messages. I know you've been saying, Mr. Sadowski, we need to know about magnetic flux. Well, don't you worry. I got you. Let's talk about magnetic flux. Here we go. Here's our definition. It's the measure of the magnetic field density through a defined surface. Yeah, that's magnetic flux. You don't want to know more about it. I know you do. Right? Let's draw some pictures. Let's say here's a surface. Maybe it's a surface outlined by a wire, maybe just some imaginary surface, I don't know. And here's some field lines, magnetic field lines, piercing through. Alright, now we've actually seen the word flux before. Back when we did Gauss's law, the original statement of it talked about the flux of field lines. Well, flux is just a word that means change. In this sense, you can almost think about it like a flow, right? So almost imagine these magnetic field lines are flowing through this surface. Magnetic flux is just a measure of how much of that surface is pierced by the magnetic field lines in this case. And the equation is the dot product of magnetic field times the A, which is the area vector, which I know sounds crazy, but don't worry, I'll explain it all. Okay? Now remember, a dot product is really just the magnitude of the two vectors times the cosine of the angle between them. So this is our equation for magnetic flux. This symbol here is the Greek letter phi. It's like a O with an I down the middle, but that's the Greek letter phi. And phi equals BA cosine theta. Go ahead and box that in as our new equation for magnetic flux. Let's define our symbols here. B is magnetic field, great. A, again, is that mysterious area vector, which I know sounds a little bit crazy, but yes, I'm going to talk about area being a vector. Theta, as always, anytime it's part of the equation, always refers back to the two previous vectors, so angle between a magnetic field vector and area vector. And again, this is phi for magnetic flux. And the units for magnetic flux are, of course, the Weber, symbolized by capital W, lowercase b. Now, if you recall, on the very first day, we talked about the Weber, right? We said a Tesla is a Weber per meter squared. Okay, a Tesla magnetic field is a Weber per meter squared. There's the definition of the Tesla in terms of the Weber. I told you it would all pay off. Okay, let's talk about flux again. Let's draw some more pictures. Let's say we have a whole bunch of magnetic field lines all pointing to the right, a uniform field, and we're going to look at a surface in different orientations. And we're identifying the area as a vector, which points perpendicular to that surface, which I know sounds crazy, but here's how it works. So pause the video if you need to, draw some pictures. Okay, so here's this rectangular surface sort of drawn in 3 dimensions, like perspective. We're going to tilt it to different angles here. And so in this first situation, here's the area vector, perpendicular to the surface. So here's the surface. Here's the front side. Here's the back side, the near side, the far side. Here's the area vector. This is going to be BA cosine of 0. The area vector points to the right, the magnetic field points to the right as well. That's a 0-degree angle between them. In this second picture, we've tilted the surface, so the area vector gets tilted as well. Now there's this angle theta between them. So it would just be BA cosine of this angle between the magnetic field vector and the area vector. In the third situation, we've turned this surface so it's completely flat horizontal. Right here's the near side, there's the far side. And now, since the area vector is perpendicular to the surface, you can see it is also perpendicular to the field. There's a 90-degree angle between the field and this area vector. Cosine of 90 is how you calculate the flux through it. Now you should be able to see that the magnetic field is pointing to the right, and since the surface is horizontal, literally none of those field lines are piercing through. And that makes sense. Cosine 90, of course, is 0. This would be 0 flux. But in this orientation, all the field lines that are there that are possible could pass through. That's an angle of 0, cosine 0 is 1. This is the maximum flux you could possibly get, and then this is just something in between. This is max flux, which I just think sounds really cool. Okay, so again, sort of like how much of these field lines are sort of flowing through, piercing through. Here, none of them are. They're passing right by. Here, all of them are. And this is just something in between. All right, what do we do with this idea of flux? Well, it was Faraday who figured out some important stuff. And here's Faraday's law in words. Any change in magnetic flux per unit of time through a loop or coil of wire will cause an EMF. He figured out that if the flux changes, it actually causes an EMF, a voltage. Interesting. All right, so here's the equation in symbolic form. Now, don't write it down just yet. This is the average induced EMF caused by a change of flux, change of magnetic flux per time, right? But it might just be just one loop or coil of wire. It might be N loops. So capital N here stands for how many loops. The more times the wire is looped around, the more field lines could pass through, and so, right? So that's going to be increasing the average induced EMF. And then there actually is a negative sign here. So here's the final version of Faraday's law. This is the way I want you to box it in. So E average equals negative N delta phi over delta T, change in flux with respect to time. Let's define our symbols here. Again, this is magnetic flux in Webers. T is time in seconds. Capital N, that's the new one. This is the number of turns in the coil, however many times it's looped around. And E average is the average induced EMF. This is Faraday's law, that any time flux changes with respect to time is going to create or induce an EMF. Our version of the equation is a delta phi over delta t, so it's an average EMF. In other courses, you might have a slightly different version of it. You'll get to more complicated versions, but at our level, it's going to be an average EMF. Now, flux, remember, is BA cosine theta, which means if we're looking at the change in flux, there's really three different ways it could possibly change. I mean, just look at the equation. There's B, there's A, there's theta. If any one of those changes, the flux will change. So a change in magnetic field creates a change in flux, that induces an EMF. A change in the area changes the flux, that induces an EMF. A change in the angle, which means, like in the pictures before, if you were to rotate the loop of wire, change in the angle, that changes how many field lines pass through, that changes the flux, that creates an EMF as well. Let's go back to the area as a vector, which I know is a bit of a weird idea. Before we said it's perpendicular, or as we say, normal to the plane of the loop, but we can get a little more particular, because in any plane, there's really two directions normal. Like if you have a horizontal plane, up is normal, but down is normal as well. Which one is it? Well, it turns out it comes from the right-hand rule shortcut, which you might recall is you point your fingers in the direction of the current around the loop, and when you stick your thumb out, that's going to be the direction of the area vector, normal or perpendicular to the loops, very specifically following the right-hand rule shortcut. So let's apply this to a situation, a very familiar situation. Let's draw this again in our notes. We've seen this before. And we're looking down at the situation. We've got our movable conductor sitting on top. Remember, we're looking down at these. Are sitting on top of these metal rails, these conducting rails, connected by a resistor, all inside a magnetic field running into the paper. The length L is the distance between the rails, and the bar is going to be moved to the right. So we already know what's going to happen. We've already gone through this. If you look back in your notes, we see that if we look at the positive charges sitting inside this magnetic field moving to the right, they're going to be forced to the far end. That's going to become positive. It's going to become negative. It's connected through the resistor, and so charges are going to flow generally around in this direction in a counterclockwise way. But now we're going to apply Faraday's law to this situation. Faraday's law says that the flux has to change. That's going to be a change in field, or a change in area, or a change in angle. Well, let's see what's happened. Let's draw this bar just sometime later, as it travels some distance delta x from its original position to its final position. By doing that, what has changed? Well, we haven't changed the field strength, right? The field is produced by some laboratory magnet, and we're not changing that. We haven't rotated anything, so it's not changing angle. It must be a change in area. Can you see that here's the original area? When the bar was over here, the length times some dimension x here is the area. And now that I moved it over here, we've included more area. Here is the original area of the loop. Here's the new area of the loop. And this here is the extra area. So the area is this length times this dimension, x, and so the change in area, this extra bit here, is L times delta x. Can you see that, right? Here's the original area, here's the new area, and this is the change in area, the extra area we add in by moving the bar from here to here. All right, let's write down Faraday's law, that EMF equals negative n delta phi over delta t. Now phi, magnetic flux, is BA cosine theta. What's changing? It's only the area. So the B is constant, and cosine theta is constant, so I'm going to pull them to the outside, right? So it's a constant B, it's a constant cosine theta. All it's really changing is the area bounded by the loop. But we have to know the direction of the area vector. So here's where that right-hand rule comes into play. All right, so we know charges are flowing around this way in a counterclockwise way. So you're going to take your right hand, you're going to follow the charge around with your fingers, like this, and stick your thumb out. So if you do it with your paper, you should have your thumb pointing out of the paper. If you do it with the screen, you have your thumb pointing out of the screen. So the area vector points out, right? Follow the charge around this way, your thumb points out towards you. The magnetic field points into the paper, the area points out of the paper. What's that angle between them? That's 180 degrees, right? Between in and out, 180 degrees. So that's going to go in here for theta. So here we go. We have negative NB cosine 180 degrees. Delta A is L delta x. That's going in here, L delta x. Let's see what happens here. We've got a negative here, cosine 180, that's negative 1. And wait a second, delta x over delta t, what's that? Well, I hope you said V bar. If you didn't say V bar, it is March. What are you doing? We know delta x over t is V bar. But let's assume it's going in a constant speed, so we're going to drop the bar. But hey, I did ask for you what delta x over delta t is. You better have said v bar. Okay, so we're going to drop the v's going constant speed. So there's a negative sign there. There's only one loop of wire. It's not coiled around a bunch of times. So capital N is just 1, and cosine 180 is negative 1, and this is v. And negative 1 times negative 1 is positive 1. And oh, look what we get. We get EMF equals BLV, which makes perfect sense because, hey, we already derived this equation for this exact situation. All we're doing now is applying Faraday's law. So the same situation, we get the same results. We should have gotten that. That's good. That makes us feel good because we should be able to apply different methods of attack to the same situation and get the same results. But the point of Faraday's law is that it doesn't have to be a change in area. It could be a change in the field, or we could rotate this whole thing in the magnetic field. Any way we do change in flux, we'll induce an EMF. We'll create a voltage without the use of a battery. That's pretty cool stuff.